to kind of start from a historical perspective, we have the concept of a database is super simple. The idea that you have some sort of data, you want to put it somewhere and it's going to stay there for a long time. We've had these for ages. This is what drives half the internet. Like Facebook is one gigantic social database. Netflix is one gigantic movie database. Like this is the core concept of how computers operate. But traditionally, they kind of just exist centralized, and that means that one person or one company or whatever ends up controlling them. Twitter is a database of tweets that Twitter controls. They basically are the gatekeepers. They allow you to change a very specific part of the database, which is the tweets that you own, and that's it. And they could revoke that right whenever they want. That's kind of the power of being a portal that you lend access to. And so in technology, once you have this database, it's very easy to just put it on one computer, have it run, put data there, and take it out. But that doesn't really scale. And so we started inventing ways of having a bunch of different computers all joined together into one network to have a distributed database. So if one computer dies, the whole network still functions. And this is still under the control of one person or one entity or one cloud provider or whatever. And so it's more of a scalability, resiliency feature. And so that has also been around for ages. The unique thing, the paradigm shift that occurred in 2008, if you want to remember 2008, I remember like the Black Eyed Peas song, like 2000 and late, because it was like November 2008, right at the end of the whole bank bailout nonsense that Satoshi Nakamoto, random person from the internet, potentially multiple people, that's a whole rabbit hole as well, if you want to get into some weird conspiracy stuff. They released this paper onto a mailing list, and it described a model for taking a distributed database and making it so that no one person owns that database. More importantly, it creates a method for everyone to have some % share over ownership of that database. And this is what we call trustless, because you don't have to trust the other people in the network in order to have that whole network operate correctly. Everyone's kind of looking out for their own. And because of that, because of this kind of checks and balances of everyone looking out for their own interests, you have a database that's not owned by any one person. It's owned by the superset of everyone in the network. And the structure for doing this is called the blockchain. It's this concept of you have some state, and then you want to make changes to it. The changes to that state have to reference the previous version of the state. And that creates a chain of blocks all the way down into the beginning of history, which is the Genesis block. And that is a very succinct way of saying that once some state has been changed, it's been kind of added to this log. You can only add things to the log, when we'll get to why that's possible. You can only add things to this log. But once you've done that, it's kind of just there forever. The whole network is kind of incentivized to keep that log around for as long as possible. So that's really neat. That's immutability. That's the ability to put some data out there and have it stay there and not change, and be resilient to any sort of attacks. And so what he did was use this technology to create a database, and then in that database, we just track the idea of how much money someone has. That's it. That's Bitcoin. Like, there it is. It's literally just, I have an address, I have this much money, you have an address, you have this much money, and then when you want to send money to someone else, you create a transaction, and we'll get into the cryptography behind this, but it basically says, I, as the owner of this amount of money, authorized to send this much from me to this other person, and then everyone in the network is in charge, excuse me, everyone in the network is in charge of verifying that, because it's in their self-interest to do so. And people called miners are in charge of doing the actual verification and computing these hashes, and we'll get to proof of work as well. But yeah, that's really it. It's a database with a very fine layer of control over how it's allowed to change. And so that's super, super interesting. And kind of an inherent property of these decentralized networks is that because no one owns them, you can't really use them for free because you are just using someone else's computer at the end of the day. And that's why Bitcoin and decentralized networks go, or rather the idea of a native currency and decentralized networks go together really well, is because to stop someone from attacking the network, DDoSing it, making it unusable for everyone else, it has to cost money to do so. And so miners don't accept transactions that don't pay enough money. And so this creates this really interesting economic market of how valuable is it in order for you to use this network. And that's the transaction fees that you kind of know about. To send money to someone else, you have to pay a transaction fee. And that's simply how much it costs to use someone else's computer to verify this thing and send it to the network and have everyone agree on that. And so that's kind of why this concept of currency and decentralized networks are so tightly connected. And as you kind of explore the space, you'll see this over and over again, is this concept of you have to stop people from abusing the network. And one of the ways people abuse the network is what's called Sybil attacks, where you just create multiple identities. And because no identity is tied to the other one, you can basically DDoS the network through creating a bunch of transactions or whatever. And so the idea of saying, hey, it costs money to do anything here, pretty much stops that, because it doesn't matter how many identities you have, you still have to pay all the money for them in order to craft transactions or do whatever you want. And so that's kind of an inherent way to stop that. So that's why transaction fees exist. That's why currency is so tied to this. So that was Bitcoin. That's launched in 2009. Very cool. I didn't know about it until recently. So it's it's very interesting to think that that was almost 10 years ago, and kind of how much has changed since then. But before we get into kind of taking Bitcoin further, let's talk about the basic cryptographic kind of principles that makes this all work. And this is super old stuff from the 70s and the 80s that people are rediscovering. They're oh, we figured this out ages ago. What? And it turns out to be still super useful. It's the backbone of kind of how computers work, how the internet works. The green check mark or the green lock at the top of your browser window is the same cryptography that's used in Bitcoin. Just the idea of saying that yes, this person is this person and they can prove it with some dumb math is really, really interesting. And so you can kind of, yeah, I guess I'll just break it down. The cryptography is interesting, but at the end of the day, unless you're specifically interested in it, the properties of it are what's more interesting. But in Bitcoin's case, well, everyone's case really, the way the cryptography works is you have this super long secret random number, and you generate this however you want through sampling atmospheric radiation or just hitting numbers on your computer, moving your mouse around. You get some randomness. And then from there, you can derive a secret key. And this is just a equally large random number. The idea is that no one else in the world knows this random number and could not feasibly generate it given infinite time. So it's impossible for anyone to get to accidentally generate the same random number as you. That's a core principle. That's really, really interesting from a kind of universal perspective. Is this number is truly unique in the universe. That's really interesting. But turns out it's not hard to do. You just move your finger around on the mouse pad for a little bit and you've created a number that hasn't existed before. That's pretty cool. And so from there you have this secret random number. And if you think about it, because no one else has this number, that number is your identity. The fact that you have that number is enough to prove who you are. And so you can take that concept and start using it to have this concept of self-sovereign identity. The idea being that you don't have to go to the government and ask who this person is. You can simply ask them to say, hey, are you this person that has this secret number? And then they can do some cryptography that we'll get into and prove it to you directly without a third party. That's really interesting, especially from a sort of like philosophical perspective, not requiring a third party to prove who you are is super interesting. We all carry driver's licenses, ID cards, passports. Theoretically, you may not need that type of identification in the future if you can just prove who you are using cryptography. And that also gets into a rabbit hole of cryptographic identity and self-sovereign identity. But referring to people by their private key doesn't work, because if I tell you my private key, now you know it, and now it's useless. So what you can do is generate a public key. And this is using a trapdoor function. A trapdoor function is just a normal sort of mathematical function that is basically one way from a computer's standpoint. It's one way. And the way that, basically it takes a bunch of data and brings it down to a smaller amount. By losing this data, this extra stuff, it makes it really, really hard to go backwards. Kind of like a trapdoor. If you fall through the trapdoor, you're not getting out. And so that's kind of the sort of baseline for all this like proving, how this proving works, is you can say, well, I'm able to generate this public key and then sign things with this public key. And signing things gets into like modulo math, and I personally am not very good at that. But it allows you to create this public identifier that you can share with people because it's really impossible. It's really, really hard, like trillions and billions of years hard for them to take your public identifier and guess your private key. And so that's why it's okay to share them. So if you ever use Bitcoin, you have a Bitcoin address. That's your public key. It's simply derived from that absurdly long private key, random number that you generated, and then turned into this very short string that has lost information, but is still perfectly unique, because turns out, like, what is that, 240 characters or something? Like, that's a lot of data that you can put in there, and it basically becomes like globally unique as well. And so no one will have a, what do they call this? What is it called? Where someone gets the same public key as you. What is that called? Clashing? No. Anyway, that won't happen because there's so much potential data there that the chances of that happening are 0.00001. Like it's so minimal that you can basically assume it will never happen. Cool. And so now we have this public identifier that we can hand out to people, and then when they want to say, oh, are you really this person, you can sign something with your private key. So you can prove that you own a private key without revealing it. And that's really dope. And so that gives you this idea of self-sovereign identity. And so when you're sending a Bitcoin transaction, you sign the transaction and you say, I am this address, here's proof, here's mathematical proof, and you can't fake this proof without having this random number. And then you can give that to everyone, and they can be like, well, yes, you are, and I don't have to go ask anyone else because you've proved it to me by doing this operation, this math operation so quickly. You obviously did not do this over the last like trillion years. It didn't take you a trillion years to sign this transaction, therefore I can be 99.999% confident that that's you. And so that gets you the ability to prove your identity. And so from there, you can start doing this concept of proof of work, which also uses these trapdoor hash functions. It's a little less, I'll just skip over proof of work. The idea is that by running this hash function, which is very quick, it's a very quick operation to do this hash function on the order of a few milliseconds. It's completely impossible to do the reverse in a trillion years. And so what people do is they run this function over and over and over again on the Bitcoin blocks in order to get a random number that just happens to be less than some arbitrary difficulty number. And so I'm kind of throwing a lot of ideas all of a sudden, but the way proof of work works is by doing this math problem over and over again, you have proved that you have done work. That's basically what you've done, is you've proved that you've burned money in order to get this random number, because there's no way to shortcut this process. you have to brute force it. And it's just over and over and over and over again. And in Bitcoin's case, you do that for about 10 minutes. And you just do the same operation over and over and over and over again for 10 straight minutes until maybe within 10 minutes, maybe it's 20 minutes. It's completely random. It's a poison process. You get this number that happens to be correct. And so that's proof of work, is by using statistical randomness, you can prove through some probabilities that someone has burnt enough money to do this. And so that's the process that allows a bunch of different people to have ownership over this database. So as you're burning money doing this hash function, once you get the valid number, whatever number it happens to be, now you have the right to append things to the database. And that's it. That's proof of work. And so when you send a Bitcoin transaction, this is sort of the life of a Bitcoin transaction, is you construct this payload. It says, this is me, I have this much money, and I would like to send it to this person. And then you sign it. And that appends a little proof that says, I am this person, and therefore I have the authority to spend these funds. And then you send that to someone in the network that you're connected to. And they can say, okay, sweet, yeah, this looks good. I agree that you are this person. They'll send it off to everyone that they know. And so by gossiping this transaction around the network, eventually everyone knows about it. And everyone agrees that, like, yeah, that's cool, this is you. But it's still not in the blockchain yet. It's not there. It's not immutable yet. Then the miners who are constructing these blocks, they're running this hash function over and over again. They're trying to get this random number. Once they do, they can include your transaction. Well, they include your transaction beforehand, and then they do the hashing. And then once they have a valid block, they then publish that to the network. And through the same sort of gossiping way, like soon enough, everyone knows about this block, and everyone can very easily check that, like, yeah, they did this math for 10 straight minutes. They burnt a shit ton of money to say this thing. Therefore, it's probably correct. And add it to the blockchain. And now your transaction is in there. And as part of that process, what they do is they verify that, one, you own all of this money. Two, like, you are who you say you are. No money was created out of thin air. No money was like destroyed. You paid the transaction fee and so on. And they do all of this validation. And that's why Bitcoin can get away with this idea of there being only 21 million of them, because everyone on the network is incentivized to keep checking to make sure no one creates Bitcoins out of thin air. I can very easily create a transaction that says, give me 50 Bitcoins, but no one will accept it. No one in the network will be like, yeah, that's cool. No one will do that. And so that's what stops people from, like just printing money, because 100% of the network agrees that no, you shouldn't do that. So kind of taking a step back, we can look at Bitcoin as this database of accounts or identities and how much money they have. That's Bitcoin. It's really just that. But turns out databases are good at storing pretty much anything you want. They could store not just money, but also how many votes are on a proposal for the government, or literally anything. Like, you could store movies or tweets or whatever. And so Ethereum is kind of born out of this idea of, what if instead of just tracking money, we tracked whatever people wanna? And that's Ethereum. It's Bitcoin, but take away the currency and then add it back and then allow everything else. And then create a programming language on top of that that lets programmers write the rules for how this database is allowed to be changed. In Bitcoin, these rules are hard-coded. It's just money. You can send money from one person to another, and that's basically it. There's some more stuff you can do, but that's it. But in Ethereum, it's quote-unquote Turing complete. It's a full programming language, and that opens up a lot of potential. So, like, not only can you send money to people, you can also do voting. You can also create markets that don't have for example, the NYSE, the stock exchange, is a centralized entity. You can use Ethereum to build a decentralized version of that in the way that allows you to do trading of stocks or whatever they happen to be. without trusting, the New York Stock Exchange to like hold your stocks and give you the stuff. And so that's really interesting. You can do, for example, DNS. You can build DNS on top of Ethereum by simply saying, hey, this contract, and that's smart contracts, we'll get into that, by saying like, hey, in this database, instead of storing money, let's store an identity to a domain name. And now this identity can own this domain name. And now they have the right to transfer it to someone else, or like add a resolver that says, hey, this domain name should go to this website, or like, here's where you find the JavaScript to load this page. And so now you've basically built DNS, but it's running on tens of thousands of computers around the world and is more resilient theoretically to attacks. And if Google goes down, Ethereum still works. And so that's really cool. So much like Bitcoin, Ethereum also has to solve the same problem of stopping people from attacking it, stopping people from DDoSing the network, making it unusable. And so they also have this concept of a currency called Ether. Ether is used to pay for things on the Ethereum network. In Bitcoin, paying for things is literally just paying for a transaction. So there's only one concept of a transaction fee. This is how much it costs to send money from one person to another. That's really all you have to worry about with Bitcoin. With Ethereum, because you can do arbitrary things, it ends up being very hard to calculate how much should it cost for you to do this. For example, adding two numbers. How much does it cost to add two numbers on Ethereum? Or voting on a proposal for a decentralized organization to allocate funds to a new nonprofit. Like, how much should it cost to do that? And so they kind of take this broad concept and break it down into computer operations, the actual opcodes that are being executed by all 10,000 computers around the world. And you pay for each one of those opcodes individually. And that is the concept of gas. Gas is how much each opcode costs to run. And so adding two numbers is pretty easy. It costs a small amount of gas. Running a cryptographic operation like signing a payload or, well, you don't sign things on Ethereum, like recovering the signer from a payload, that costs a bit more gas, and so on. And so your transaction, as it does all these different things, ends up having a total gas cost. And that's just how they measure your impact to the network. How much of the network are you using? And that's denominated in gas. And so much in the same way as Bitcoin, where if the network is being used very heavily, people are paying X amount of dollars to use the network. If Bitcoin starts running out of space for transactions, you can pay more to get your transaction in, and you create a market around transaction fees. And so that's what happens when you hear people say like, oh, transaction fees are at like $20 because they were in December. And I know that because I gave my uncle some Bitcoin for Christmas, and it cost me $20 to send him $100. Like, what? Same thing happens in Ethereum, except it's denoted in gas because there's infinitely many more things you can do. And so Ethereum also has what's called a gas price. The market has decided that one gas costs this amount of Ethereum or Ether. And that fluctuates up and down, but it's very similar to Bitcoin. You can think of it as just a tax to use the network to use other people's computers to verify what you're doing. And so that ends up being, anywhere on the order of like cents to dollars, depending on what you're doing. If you're running like an incredibly complicated thing, it might be $100, but that's pretty much the top maximum thing that I could imagine doing. Like normal sort of operations are less than $1 for now, at least. Like, depends on the network. And so with Ethereum, you have this database that can store arbitrary things and a programming language that lets you decide how that database is changed according to, however you write your code. It's very open. You can do whatever you want. And that gives you a lot of cool things philosophically. It gives you immutability, that same immutability that you get by using a blockchain and proof of work. Once you have changed something, it stays there. It can't be changed again unless your code allows that to be changed. And even then, the historical state is kept. So you can always roll back time and see, hey, how much money did this person have at this time, and so on. Or even in the case of like voting on something, you can roll back and say, how many votes did this have right before it closed? It gives you censorship resistance. These changes that you're making to the database are run by 10,000 computers around the world. That makes it really hard for someone, potentially even a government, to attack it and stop that code from running. That's really, really cool if you get into the whole privacy, censorship resistance, and kind of philosophical side of that. The ability to run code without anyone stopping you is really dope. It opens up a lot of it just opens up a lot of possibilities there. And so in a lot of different cases, censorship resistance isn't specifically necessary. For example, like I don't need censorship resistance for voting on my local community's garden, like what are we gonna plant in the garden? I might want censorship resistance if I'm whistleblowing and want to post something, I wanna post some sort of document to the network and I don't want anyone to stop me, awesome. Or like if I am sending money from one person to another, and traditionally, government can lock your accounts, they can stop, banks can do all kinds of nonsense to you. Censorship resistance is really valuable for money. The ability to say, this is my money and I have the right to send it to anyone else without permission is dope. And so that's its own rabbit hole as well. And so similarly, self-sovereign identity, we covered this before, the ability to say who you are without asking someone else is really, really cool. It lets you own things, it lets you own digital things without asking someone else, much in the same way that when you tweet something, you're asking Twitter to, hey, put this in the database for me and then send it to all of my friends. You don't have to ask them to do that anymore with self-sovereign identity and self-sovereign ownership. You can truly own your Twitter profile or your Facebook or your YouTube, etc. And YouTube can't take down your videos now. Like, that's dope. You can get digital scarcity. Digital scarcity is the idea of write some code that says there will only be 10 of these things, whether they be tokens or digital cats on the internet. There's only 10 of them. And because 10,000 computers around the world are double checking that every block, you can be reasonably certain that there will only be 10 of them. And that's really, really interesting because before you could not have digital scarcity. It was simply not possible. Photos can be copied and pasted. They can still be copied and pasted. Licenses can be faked. Like digital game items can always be created by the publisher. You have no digital scarcity, but now you can. And that opens up a lot of possibilities, especially for art. The ability for digital art to be valued on par with physical art is kind of like market changing. Like it is a paradigm shift in how people view digital art. Because finally, you have very much the same properties as physical art. You can produce exactly one of something and then sell it, auction it off. Or you can produce versions that are numbered or perhaps not. And like maybe some of them have defects. Like you can very closely match why people want physical art in digital art. And that's really interesting. Same thing with game items. You have digital game items, these digitally native assets that people own, but they don't really own. And so because people don't own them, it's actually kind of surprising that they're worth money. Like if you look at Fortnite skins, for example, Fortnite's very hot right now. Like those cost real money and people value them, even though they don't own them. Fortnite could take them away at any point. But with true digital ownership, you have the ability to actually own that outside of Fortnite, the publisher's control. And that's awesome. That gives you the ability to actually value this digital thing. That's like what's really exciting to me about this whole space is like true ownership of digital things. Digital things being identity, kitty cats on the blockchain, or currency altogether. And you can also do this concept of atomic swaps. The way like Ethereum works is if your transaction is progressing along and it's doing its thing and it's updating the database and it's sending money to this person and sending money to this person, and then it encounters a problem, it doesn't just fail, it reverts everything before. And that way you can be 100% certain at any point in time that if your transaction succeeded, everything that happened within it also succeeded. And that allows you to do this really interesting idea of an atomic swap. The idea of, I have this thing, you have this thing, and we want to trade, but we can't trust each other. Like in a normal world, like if I want to trade this to someone else for this, I have to put this down onto the table, and then they put this down onto the table, and then I grab this and they grab that, and we've traded. But there's this risk involved. They could take my paper and run off with it. And that's why people use escrows. That's why people have trusted third parties for wills, et cetera. You don't need that with Ethereum. You can just say, you can just write some code that says, hey, take this from this person, swap it around, and then finish. And then if either of those two things fails, like this person rejects the paper, or like maybe there wasn't enough money involved, the entire thing fails. And that's really powerful, especially for economics, and especially for markets, and the ability to, you know, just trade things. Cool. So now that we have this idea of why this is philosophically cool and kind of the ideas behind it, you can start building apps on top of it. And people use the word DApp, decentralized app, to decide, they just decided that. I can't wait for that word to go away. But dApps are just normal apps that everyone knows and loves, normal web apps or command line apps or phone mobile apps that just happen to talk to a decentralized network for 100% of their operations or 1% of their operations. Doesn't really matter. If you talk to a decentralized network, you're a dApp. And so that lets you do really cool things, like, for example, with trading tokens. And actually, I forgot to mention this. Tokens on Ethereum are not special. They're also just code. It's literally just some code that says, well, what if we take Bitcoin's model of addresses to balances and write that in Ethereum? That's what people did. And now a token is literally just a database that says, this is your address, your public key, and this is how much of this token you own. That's it. And then it does that for everyone else in the network. That is a token. It's like 10 lines of code. I could write it on the board right now. It's literally just a database and then some functions that allow you to add and subtract to transfer money from one person to another. Tokens aren't special. And that was actually a really key insight for me when I was learning about all of this. I was like, well, what is a token? Turns out it's just code. And if you understand code, you understand tokens. And so, yeah, you can interface with the Ethereum blockchain, or any of them really, by using by just talking to a node directly. And so you can either run this yourself on AWS or on your laptop or whatever, and go talk to it over an API. If you've used an API before, it will be incredibly familiar. It's JSON RPC. You send it commands, it gives you stuff back, and you say, hey, how much money does this person have? They have 2 Ether, sweet. What's the state of this contract? It's this, sweet. Or here's a transaction, broadcast it to everyone, please. Sure thing. Like it's just like that. So if you've ever used any sort of API, it's incredibly similar. And so you can start using that to build apps. And so one of them is 0x. It's a way to transfer tokens between people using that atomic swap property that I demonstrated earlier in a very nice way that lets you create markets and trade very quickly, but you also get the guarantees of atomic swaps. No one can back out of a trade. No one can like reject your trade and take your money. That's really cool. And so they have a little website that says, hey, post an offer or fill an offer, and then you post an offer and it goes onto the blockchain. And then if you want to fill it, you send craft a transaction, send it to your Ethereum node, and then it goes off and does its thing, swaps it around, and now you own whatever you wanted in exchange for whatever you provided. You can build voting apps, and you can actually take this idea of voting to kind of its logical extreme and create a government on chain. The idea being that you create an app that allows you to vote on things. It allows you to allocate funds. It allows you to do, whatever else the government does. But it talks to Ethereum for important things like who voted for what? How much money does the treasury have? Did we agree on this last time? And so you write this normal app, And then it talks to Ethereum for trusted state that you have to have 10,000 people in the world verify. And so that's really cool as well. Now this government body is censorship resistant, it's immutable, it has self-sovereignty, it can operate on its own, kind of outside the jurisdiction of anything else if it's totally autonomous. Or you could also just use it to plan your neighborhood get-togethers. Like it's really interesting because it's useful on one hand, but then it's also like censorship resistance, and now you can operate outside the government's control. You can create markets and everything. You can also do curation. I noticed that on the board over there, there's some documents about curation. When you have these sort of totally decentralized things where one person, there's a bunch of people on this side that don't know each other and a bunch of people on this side that don't know each other, and say you want to create a social network, if you don't have a good way of surfacing good content, you'll just get bad stuff. If people are allowed to be anonymous on the internet, they can do whatever they want. They will do whatever they want. And this is not great for a social network because now you get spam, but it's also not great for economic markets. So if you're just building a stock exchange, or you're trying to do some sort of, literally whatever you want to do, you have to solve this problem of curation, this idea of finding the signal in the noise. How do you get people to curate? And we do this, humans do this all the time. When you like a tweet, you're curating. When you upvote a post on Reddit, you're curating. When you add something to your Spotify playlist, you are curating. And we do that for free right now. But there are some areas where you might want a high guarantee of this information being accurate. For example, one project is trying to categorize locations on Earth in order to just make a really good curated set of locations that are, for example, restaurants, or are amusement parks, or are places of interest. And so they have to solve this curation problem, because if they don't, people will just say this is the #1 spot for sushi in San Francisco, but they own that place. So of course they'd say that. You have to get a bunch of people to agree to curate and say that, oh yeah, that place is #1, or no, it's closer to #4. And so they're working on this. They're building this concept of a token curated registry. The idea that using economics, you can get people to collaborate and curate something. And so that's super interesting as well. But curation is kind of an open, hard problem with these decentralized networks. And so that's definitely something that centralized social networks are really good at, is Facebook doesn't like something, ban them. Twitter doesn't like this, remove them. Delete the post, you can report people. That's all really useful. But with a decentralized network, you kind of have to rebuild that in a kind of decentrally native way. But yeah, so everything's just a smart contract. Writing smart contracts is relatively easy. Writing them well is relatively hard. For that reason, there are a lot of kind of tools and everything to help you write them, because if you're managing money and you get it wrong, that's not good. And so tools like OpenZeppelin are repositories of good code that you can learn from or use. And there's a few different projects like that. And they're tooling like Truffle. We have some listed on the toolbox over there. Truffle and Blockstack and IPFS. Those are all different tools in your toolbox for doing things. Truffle is really good. It's just a framework. It's a structured way of writing smart contracts and then deploying them. Because you can do this kind of on your own. You can write a smart contract in this language, compile it, and then craft a transaction and then send that to the network. But that's just such a pain in the ass. No one wants to do that. And so Truffle makes it easy. You do Truffle deploy, and now your contracts exist. Or Truffle migrate, and now they change. And so Truffle's pretty indispensable. Yeah, I'm not sure what else I have here besides security is hard. So that's kind of like a big topic is, yeah, managing money. You got to be very confident about what you do. And especially because this code that you send is immutable. It's, once you put it out there, it exists forever. And anyone can use it anytime they want. That's kind of the whole point, right? If you make a mistake, it's still there. You don't get to like upload a new version and point your website at it and have it fixed. It kind of just sits there. And we have different ways of, solving this, but it's kind of a fundamental aspect of an immutable piece of code, is that if it's got a bug, that bug will stay there. And so that's actually historically relevant. Some people published a buggy piece of code that managed the wallets of a bunch of different projects. And then someone accidentally deleted that code, because you can actually delete code, which is sort of ironic, but a contract can delete itself in a very specific setting. Someone accidentally deleted that, and now there's a bunch of money just sitting there with no code to control how it's moved, which is hilarious if you think about it. But it kind of talks about the immutability, the kind of, this code now lives on its own. No human can go in and say, hey, I want my money back, because there's no code that says, sure. It's literally just, it's there, it exists, and it is frozen, basically. And that's kind of hilarious. Oh, I could talk about browsers. So if you make an app, it needs a connection to an Ethereum node. Not everyone has one running on their laptop. I don't. So what people have are little Chrome plugins or iPhone apps or whatever that provide an Ethereum connection to whatever you want. So you'll quickly find that there's an app on Chrome called MetaMask. It's on Firefox and everything as well. And all that does, and it seems really magic, all it does is inject a link into every web page you visit that says, hey, if you want to talk to Ethereum, use this link. That's it. And then you go and talk to it with the normal API. And so if you're writing an app that wants to display how many tokens you have or what the state of the network is, you can use MetaMask, and your app will just have a connection to Ethereum. And that's really useful for developers who don't have to kind of run their own all the time. But yeah, thanks so much for being here and listening.